Good morning to all. Today I am going to discuss about magnetic materials. So first in this introduction I have to tell. So magnets or magnetism concept is not the recent topic. Magnets have been known for centuries. The Chinese and Greeks knew about the magical properties of magnets. And our ancient Greeks used a stone substance which is called as magnetite. So magnetism is not at all the recent concept. Our old Chinese and Greek people, they used the stone substance which is nothing but magnetite. They discovered that this stone substance always pointed in the same direction. Later, these stones of magnetite called lodestones, which were used in the navigation process. Next, William Gilbert, an English physician, first proposed in 1600 that the earth itself is a magnet, and he predicted that the earth would be found to have the magnetic poles, say north pole, south pole, like that earth itself is going to be a big magnet, and which itself is also having the magnetic poles like north pole and the south pole. Then what is magnetism? Magnetism is nothing but the force of attraction or repulsion of a magnetic material due to the arrangement of its atoms, particularly due to the electrons. How the electrons are arranged inside the atom, depending on that it has to exhibit either attractive property or repulsive property. That property it is to be called as the magnetism. Then in other way also we can define about magnetism, the phenomenon of attracting magnetic substances like iron, nickel, cobalt, etc. That is to be called as the magnetism. And moreover, this word magnetism was coined from the name of the iron ore, magnetite, Fe3O4. In the previous slide I said ancient Greeks used one stone substance, what that is to be magnetite. From the same magnetite only this word magnetism was coined. This magnetite is a big stone substance used by our ancient Greeks. Two peculiar properties it has to exhibit. But those two peculiar properties in the sense it always has to align in the same direction from north to south. What the second property is to be, any iron, small pieces of iron, if we have to bring near to this stone substance, it is to be attracting towards those small pieces of iron. These are the two peculiar properties exhibited by the stone substance magnetite. Because of this magnetite which is exhibiting those two properties, so that our phenomenon of attracting magnetic substances is also to be named as magnetism. So attraction property towards iron based substances or nickel, cobalt, etc. is to be known as the magnetism. In this contents I am going to deliver here is to be basic definitions, origin of magnetism, hysteresis curve, hard and soft magnetic materials, at last is to be ferrites and their applications. First we have to start the basic definitions. In magnetism so many basic definitions are there. First we have to understand those, then only the remaining concepts are understandable. That is why first basic definitions we have to start. In that the first one itself is to be magnets. Magnetic material, other words shortly we may call magnet. Then what is a magnet? Materials which gets magnetized when placed in an external magnetic field are known as the magnetic materials. Two ways I defined here. The first way of definition is so materials once they are placed in the external magnetic field, once placed in the external magnetic field which are getting magnetized, those substances are known as the magnetic materials. So in other words also we can define this magnetic material. This is routine way of definition. Materials which strongly attract the small pieces of an iron are known as the magnets. So which attracts small pieces of iron, that are known as the magnets, or which when gets magnetized when they are placed in the external magnetic field, that are also called as the magnets. Once we have known about the magnetic material or magnet, then oppositely also we have to define what that is to be non-magnet. Non-magnet we have to define. Non-magnets are nothing but materials which doesn't get magnetized even when they are placed in the external magnetic field. Here also two ways of definitions I have given. First is the terminal. Once those are placed in the external magnetic field which doesn't get magnetized, those are known as the non-magnetic materials. So other routine way is to be materials which doesn't attract the small pieces of iron are known as the non-magnets or non-magnetic materials. These are magnets or, and the second definition is to be non-magnets. Then once magnetic material means definitely about dipole we come to know. Once dipole is there, then automatically dipole moment. What is dipole moment also we have to know here. First magnetic dipole, name itself is indicating two poles are to be there. Then what the two poles in magnet? North pole and the south pole. So the magnetic dipole, equal and opposite strengths separated by a finite distance is called magnetic dipole. So two equal and opposite poles separated by a finite distance is called magnetic dipole. Once dipole is existed, then dipole moment is to be developed. What is magnetic dipole moment? That we have to come to know here. The magnetic dipole moment is the product of the pole strength and the separation 2L between the two poles. How much is the separation between the two poles of magnet is here? Short distance, that is to be 2L. Then how much is the pole strength we have to denote is to be small m. If these two parameters are to be taken as the product, then magnetic dipole moment is to be formed. So magnetic dipole moment is the product of both the pole strength and the separation 2L between the poles. Under which equation I have written magnetic dipole moment is capital M, which is denoted by capital M, whose equation is to be small m into 2L, where small m is pole strength. Units of pole strength is to be ampere meter. Then what is meant by pole strength is to be, so the force exerted by one pole onto the opposite pole is called as the pole strength. So pole strength is denoted by small m, whose units are ampere meter. Then ampere meter is the unit for pole strength. Then length is also having, length units are to be meter. So ampere meter into meter. Then what it has to become? Ampere meter square is the unit for magnetic dipole moment. So pole strength unit is ampere meter, length unit is meter. So capital M is equal to ampere meter square is the unit for magnetic dipole moment. That is the two parameters, dipole and dipole moment. So here I have written again pole strength M, ampere meter, magnetic dipole moment capital M is equal to small m into 2L, whose units are ampere meter square. Then magnetic field, one qualitative property we have to define here, what that is to be magnetic field. It is the region around a magnet in which it exerts forces on the other magnets and an objects made of iron is a magnetic field. So the region or space surrounding a magnet, this is the region or space surrounding a magnet up to which its magnetic influence is experienced by other magnets or any iron based substance is called as the magnetic field. So like no units are to be there, like qualitatively we have to define any bar magnet you have to consider up to where its magnetic influence is experienced surrounding it. The total field we may call it as the magnetic field. Next is the magnetic flux, whose notation is to be phi. Phi is the notation for magnetic flux. It is to be defined as the number of magnetic lines of force passing normally through a surface. Once the magnetic material is subjected to an external magnetic field, it gets magnetized. As it is getting magnetized means some of the magnetic lines of force are passing through the material. Then how much is the number? Number of magnetic lines of force that are passing normally through a surface is called as the magnetic flux, denoted by phi. Then whose units are Weber or Tesla meter square. Flux units are Weber. In other words, we have to write it as Tesla meter square. Then flux is there. After that we have to define magnetic flux density. Flux density we have to define. This also to be called as magnetic field induction. Magnetic field induction, whose notation is to be B. D is the notation. Then flux density means flux per unit area. Same definition I have written. The number of magnetic lines of force passing normally through a surface of unit area. Per unit area, per unit area, how many number of magnetic lines of force passing normally through a surface. That is called as the magnetic flux density or magnetic field induction. So B we have to denote. B is equal to how much is to be 5 by A. 5 by A. 5 units already we have known, Weber. Then area units are meter square, Weber per meter square. This other words we call it as Tesla. Weber per meter square or Tesla. So magnetic flux and magnetic flux density or magnetic field induction. This I define. Next parameter is magnetic field intensity or applied magnetic field or external magnetic field also we may call, whose notation is H. H is the notation. It is the force experienced by a unit north pole placed at a point in a magnetic field. So in a magnetic field, then how much is the force experienced by a unit north pole? Between the two poles, north pole and south pole, north pole is taken as the reference. Then how much is the force experienced by a unit north pole once it is placed in a magnetic field? Is called as the external magnetic field or applied magnetic field or magnetic field intensity, whose units are ampere per meter. Then equation is to be according to definition only. Equation it should be written here. Capital H is equal to F by M. Force experienced by pole strength of the north pole. Pole strength is denoted by M. M is the pole strength of north pole. How much is the force experienced? F by M is the equation. Then whose units are ampere per meter. Then in what way we got these units is to be, then to calculate this external magnetic field intensity, assume current is to be supplied. Then how much is the current passed through unit length? How much is the current passed per unit length? Current per unit length. Then how much it has to become? Ampere per meter. How much is the current passed per unit length of the material? Ampere per meter is the unit for this magnetic field intensity. Next is the intensity of magnetization. So notation is I. Intensity of magnetization, whose notation is I. Then two ways of defining is to be there. The magnetic moment per unit volume of the material. How much is the magnetic dipole moment developed in a material per unit volume of the material? So I is the notation. I is equal to dipole moment is to be capital M. At the starting itself we have written magnetic dipole moment is the product of pole strength and length of the magnet. So pole strength and length of the magnet, that is the dipole moment. The dipole moment is considered here to write the equation for intensity of magnetization. I is equal to capital M divided by volume. Per unit volume, how much dipole moment? M by V. M units already we have known. Pole strength units are ampere meter and then length units are meter. Ampere meter square is the unit for magnetic dipole moment. Then volume units we have known, that is length into breadth into height, that is meter cube. Then I units we want to calculate intensity of magnetization, ampere meter square by meter cube. Meter square will get cancelled, 1 meter is left over. Ampere per meter is the unit for intensity of magnetization. The same here it should be written. Same units it is carried when compared to the intensity, magnetic field intensity. In the previous slide I have shown intensity of magnetic field is to be magnetic field intensity, H I defined there, force per pole strength, F by M. F by M, per that also same units it is to be carrying, ampere per meter. And then intensity of magnetization is also carrying the same units here. So it is also defined as the ratio of pole strength per unit area. Then how can it become pole strength per unit area? As I have written, I is equal to M by V. Then ratio we have to write, M equation I have to write here, M into 2L. Then volume I have to write length into breadth into height. Length is 2L, length of the magnet is 2L. Then here I have to write area. Breadth into height I have to consider area. Then 2L will cancel. Then what it is left over here? Small m by A. Small m by A is the equation for intensity of magnetization. Small m is nothing but pole strength, A is area. So it is also defined as the ratio of pole strength per unit area. I is equal to m by A. So units are ampere per meter. Next is magnetic susceptibility. So this is one of the important magnetic parameter, magnetic susceptibility, whose notation is Xi. Xi is the notation. The intensity of magnetization produced in a material is directly proportional to the applied field intensity. To write the equation for Xi, one proportionality concept we have to use. Assume a magnetic material, a bar magnet, is to be placed in the external magnetic field. It is placed in the external magnetic field. Then this magnet gets magnetized. While it is getting magnetized, whose intensity of magnetization, I, it is directly proportional to the how much is the external magnetic field intensity. Say I is proportional to H. Then to remove the proportionality, one constant we have to place, magnetic constant, or that constant I considered here is to be Xi. Xi is the magnetic constant, then I is equal to Xi into H. Then Xi equation we want to write, that we call it as susceptibility. Then equation is Xi is equal to I by H. Then I by H, units we have to check here for this. Intensity of magnetization is, so far we discussed in the previous slide, intensity of magnetization is ampere per meter, and then magnetic field intensity units are also ampere per meter. Both are cancelled with each other. Xi is not having the units here. No units for the susceptibility. So Xi is not having the units. Equation here is to be, it is the ratio of intensity of magnetization to the external magnetic field intensity. Then qualitatively also we can define this intensity of magnetization. What it should be? Easiness of the material by which it gets magnetized is also called as the susceptibility. How much easiness is there for the material towards the magnetization, that easiness is also to be called as the susceptibility. If more easiness, it easily gets magnetized, more susceptibility it is getting. Then less easiness means then it is very difficult towards the magnetization process. Less susceptibility value it has to find. So qualitatively we can define the susceptibility as easiness of the material to get magnetized once it is placed in the external magnetic field is called as the susceptibility. Then next, one more parameter. So in this magnetism is magnetic permeability, whose notation is mu. Mu is the notation for which, right, first qualitative definition we have to see. Again, proportionality concept is also to be there. The property by which it allows the magnetic lines to pass through it. Then how many lines of force that is passing through the material normally is called flux. Number of lines of force is denoted by flux. Then by which property these lines of force are allowed by the material is called as the permeability. Then permeability is the property by which the material, it allows the lines of force to pass through it. That property is called as the permeability. To write the equation for this permeability, proportionality concept we have to consider. What the proportionality? Again assume one magnetic material to be placed in the external magnetic field whose intensity is to be H. As we placed the external magnetic material, then which gets magnetized. Because of this external magnetic field, our magnet gets magnetized. As it is getting magnetized, whose flux density B changes in accordance with H. Say B is directly proportional to H. In previous slides itself I defined what is magnetic flux density also. Magnetic flux density is nothing but flux per unit area. So this once material gets magnetized, whose flux density varies in accordance with H. Same proportionality it should be used here. B is proportional to H. As proportionality we want to remove one magnetic constant, it should be placed here. B is equal to permeability mu into H. This is the magnetic constant permeability. Then or mu is equal to, mu equation we want to write here, mu is equal to B by H. Then units we have to check here, Henry per meter. Then another equation is to be there. To write this units here, what the concept it should be used. How much permeability means once we want to produce the magnetic field, we have to supply the current. Then inductor coil we have to use. Then how much is the induction per unit length? Then induction units is to be Henry. Then per unit length means length units are to be meter. Then that is to be Henry per meter is the unit for permeability is to be written here. It is also defined as the ratio of B and H. So whatever I defined previously, that is to be qualitative one, by which it allows the magnetic lines to pass through it. Then equation wise definition also we have to be written. Permeability is also defined as the ratio of B and H. Right, this is the permeability of the medium. To check units here, Henry per meter. So for writing the units for that ampere per meter, that is to be field intensity, that I have said there. Field intensity means H, I said. H units I have written ampere per meter. Ampere per meter, how I have written? Then how much is the current? Say we are producing the magnetic field. To produce magnetic field, we pass the current through the material. So say solenoid coil we have to use, to which we have to supply the current. Then how much is the current supplied through the solenoid coil per unit length? That is to be the current per unit length is the ampere per meter. Then here what the units we considered here is to be Henry per meter. Then how much is the inductance per unit length is to be considered as the permeability units. Inductor units is to be Henry per meter. That is the unit for inductor, that is the unit for magnetic permeability. Then this is permeability of the medium. Relevant to this medium permeability, still more two values are to be there. One is the permeability of free space. Then mu naught is the notation. Mu naught represents permeability of free space. Then how many are the number of lines of force that are to be passed through the free space is to be called as the permeability of free space, whose value is to be constant. Say mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. This is the standard value for mu naught. That is to be Henry per meter, 4 pi into 10 power minus 7. Then both permeabilities are there, medium and free space permeability. To relate them, relative permeability is to be used. It is the ratio of permeability of the medium to the permeability of the free space. Then according to which mu r is equal to mu by mu naught. Then no units it has to carry. Why? Because Henry per meter is cancelled by Henry per meter. Then no units for relative permeability. Then after this, relation between relative permeability and susceptibility. I define both the parameters here. Susceptibility, magnetic susceptibility Xi, and relative permeability mu r. So between both of them, what the relation that we have to derive here. So to derive this relation, one familiar equation in magnetism we have to use, where B is equal to mu naught into H plus I. This is the equation we have to use as the basic one. B is magnetic flux density, mu naught is permeability of free space, H is field intensity, I is intensity of magnetization. All the terms we have known, this familiar equation we have to use. Then in this left hand side we have to consider. First left hand side is B. B is equal to, already we have known, B is equal to mu into H. From which equation we got this is to be, we have known permeability mu is equal to B by H. B is equal to mu into H. So according to this left hand side B, I substituted mu into H. Then B is equal to, mu is replaced here as to be product of mu naught and mu r. Then mu naught and mu r. From this, from which equation I have written this is to be, in previous slide I said relative permeability mu r is equal to mu by mu naught. Then mu is equal to what it should be written, mu naught into mu r. Say in the place of mu, I have written mu naught into mu r into H. Then this is the left hand side term where I substituted mu naught mu r into H is equal to, right hand side is similarly I have written mu naught into H plus I. Say mu naught will get cancelled. Then mu r is equal to, taking this H to the right hand side, mu r is equal to H by H plus I by H. Then mu r is equal to, H and H will cancel, 1 is left over, plus I by H. 1 plus I by H is already we have known susceptibility, ratio of intensity of magnetization to the external magnetic field intensity. Mu r is equal to 1 plus Xi. This is the required relation between the relative permeability and susceptibility. Then with this basic definitions we completed. Then after that we come to know about the origin of magnetism. There are two ways to produce the magnetism inside the material. Then how it is to be origin, that that is to be explained under this here, under this heading, origin of magnetism. Magnetism can be origined in a magnetic material in the two ways. So what are the two ways means here? One is the by supplying an electrical energy. If we have to give the external electrical energy, easily the material can acquire the magnetization property. Then second one is to be with basic fundamentals only, without supplying any electrical energy, magnetism is origined in the material. How it is to be possible, that I have to explain here. So first way we have to consider by supplying an electrical energy, how the magnetism is to be produced within the material. Then this is to be the coil, we call it as the solenoid coil. In which experiment we have to use this is to be BH curve experiment. Actually aim of this experiment is to trace BH curve of ferromagnetic material once it is placed in the external magnetic field. That is the we have to trace BH curve for a ferromagnetic material. Ferromagnetic material best examples are 3: iron or cobalt or nickel. Then it is placed in the external magnetic field, it will give BH curve. Then how it has to give BH curve? Means directly it doesn't has to give. You have to place this ferromagnetic material in the presence of external magnetic field. Means we want to produce external magnetic field, for that we have to use the coil. What the coil name is to be solenoid coil. This we have to use in lab. How this solenoid coil is to be constructed? A cylindrical shaped tube it should be considered. To which electrically conducting copper wire is to be wounded some 1000 number of times. Then starting and ending leads are to be connected to a battery. Then once battery is switched on, current is passing through this solenoid coil. Then as current we are supplying, then perpendicular to the axis of this solenoid coil, magnetic field is to be produced. This is the justification for the first way of origin of magnetism. How the magnetism is origin? Means we are supplying electrical energy, in the sense current we are giving, then automatically perpendicular to that magnetic field is to be produced. Like that one experiment is to be the justification for that. The other experiment in lab we are doing is to be Hall effect. The statement of Hall effect is to be if current is to be supplied to the electromagnetic coil, then magnetic field is to be produced. In this experiment also it is required to produce magnetic field. Then what the statement of Hall effect is to be, if current carrying semiconductor is placed in a presence of magnetic field, then voltage is developed. Then in this, to do this experiment, you have to consider current carrying semiconductor. It is to be placed in the magnetic field. Then only voltage is to be produced. For that it is required to produce magnetic field. To produce magnetic field, these are the coils we have to use in the lab. What those coils are? Electromagnetic coils. Name itself is indicating electromagnetic. You supply electrical energy, magnetic field is to be produced. Again, these are constructed by wounding copper wire some 1000 number of times. Two coils are to be combined together. To this copper wire you supply electrical energy, magnetic field is to be produced. This is also another justification where the first way of origin of magnetism can be done by supplying electrical energy. Right. Next, second way we have to choose. Second way what I said is to be, so without supplying electrical energy also, magnetic field is to be produced. How it is to be produced? That is the basic concept. So magnetism also arises from the magnetic dipole moment. How the dipole moment is generated within the material? Assume one bar magnet. If it is placed on the table without supplying any electrical energy, if we have to bring small iron pieces near to it, it gets attracted to this bar magnet. Then no electrical energy we supplied, still this bar magnet is attracting the small pieces of iron. How can it should be done? Means some basic concept is to be there. Within the material itself, some dipole moment is to be developed. Then what kinds of dipole moments are to be developed in this material? That we have to see. This bar magnet itself is a material. Then material is the combination of several molecules. How it is attracting small pieces of iron means here material itself is the combination of several molecules. Any molecule you have to consider, it is the combination of several atoms. Among these several atoms, any one atom you have to pick out. In this one atom you have to pick out. About that we have to discuss. In this atom, at the center, nucleus is to be there. In this nucleus, two types of ions are presented, say protons and neutrons. These both are to be called as the nucleons. As they are presented inside the nucleus, these are to be called as the nucleons. Protons are having positive charge, because of this nucleus is also having positive charge. To be stable with the atom, already we have known atom itself is to be stable. To become atom to be stable, then surrounding this nucleus, electrons are to be revolving. Electrons are to be having which charge here is to be negative charge. Electrons being with their negative charge, these are revolving around the nucleus. Then what the sorts of dipole moment it is produced within this atom? In the sense, electrons with their negative charge, they are to be orbiting around the nucleus. These are the charged particles, they are continuously orbiting around the nucleus. They have to generate some dipole moment. What the dipole moment? We call it as the orbital dipole moment, to be denoted by mu O. O stands for orbital magnetic dipole moment. Then in addition to this orbital motion, electron, it is also spinning about its own axis. Say this is the axis of electron, you have to consider like this. It also spins about its own axis. Because of this spinning motion, this electron also contributes some dipole moment. What the dipole moment is to be? Spin dipole moment of the electron. How it is to be denoted? Mu S, mu suffix S. S stands for spin. Then these are the two kinds of dipole moments. In addition to that, nucleus being with its positive charge, assume this is the axis, it also spins about its own axis. That is to be denoted by mu N, nuclear dipole moment. These are the three dipole moments are there inside the atom. Then resultant dipole moment for a particular single atom is mu is equal to orbital dipole moment of electron plus spin dipole moment of electron and nuclear dipole moment. So these three dipole moments are considered together, resultant is to be formed. Then in a single atom, this much of dipole moment is developed, means each atom behaves as a tiny magnet. A small magnet like that each atom has to behave. Like that, number of atoms are joined together, molecule is to be formed. Molecule itself has to behave like a magnet. Then molecules are to be joined together, material is to be formed. Then definitely without supplying electrical energy, this material itself, because of with these dipole moments, number of dipole moments which are existed inside the molecule, material itself has to be behave as the magnet. No electrical energy is to be required. That is the explanation for the second way, where without supplying any electrical energy, magnetism is origin within the material. That is the second topic, origin of magnetism. Thank you.